Hello everybody, I hope you're doing great. I'm going to present my paper in 12th International Conference on Computer, where it's held at Farsi University. The title of our paper is Degarbayan-SC, a Colloquial Paraphrase Farsi Subtitles Dataset. It's about a novel dataset in artificial intelligence, especially in the natural language processing. In summary, we collected colloquial text from movies subtitles to train artificial neural networks. So at first, we will talk about paraphrase text and importance and structure. In the next step, we will talk about preparing dataset. Third, we will evaluate the quality of our dataset by training the transformer models, and we will show the results in conclusion. Okay, paraphrases differing textual realization of the same meaning have proven useful for a wide variety of natural language processing applications, such as information retrieval, text simplification, question answering, and chatbots. For instance, as you see, the original sentence is he has tons of stuff to throw away, which paraphrases he needs to get rid of a lot of junk. The structure divides to four. The first and simple one, you can change words with synonyms. Second, you can change part of a speech. For example, he won the race with difficulty, which paraphrases he won the difficult race. Third, you would change sentence structure. For example, changing passive sense to active sense, or vice versa. Fourth, you can omit or add more details. Paraphrases contain three areas: paraphrase detection to detect same contents from two or more stories; paraphrase extraction to extract sentences with the same meaning as a desired sentence in the larger scale dataset; paraphrase generation is for generating paraphrases from input sentence. As you see in the table, some large scale English datasets are shown. The preparation and construction of them are addressed. Not only our dataset is the first Persian paraphrase dataset, but also our method is different. Our method is based on aligning sentences in different subtitles from the same movie. The main idea was coming from a paper that they use an automatic machine translation in front of a manual translation and align them cent by cent. But when we have appropriate source of subtitles in Persian, and most of the movies have at least two good Persian subtitles, we don't need to use automatic translation. The advantages of our dataset are open source and easy to use with a specific timestamp. It is in colloquial language that helps neural networks to generate sentences closer to human. Movies are made every day and their subtitles are available after a few days. We use web scraping to collect our Persian movie subtitles. We crawled wordsubtitles.com web pages. Actually, we downloaded subtitles of more than 17,000 movies with beautiful soup in Python. Before aligning sentences, we deleted movies with less than 2 subtitles and the subtitles without UTF-8 encode and .srt suffix. In the next step, we aligned sentences with adding manual filters. For example, we omitted similars with upper than 70% similarity, or we checked number of different words to delete unrelated sentences. First, we could align more than 4 million pair sentences, but after setting filter, our dataset was reduced to 1.5 million good pair sentences. We normalized them and we deleted punctuation marks. As you can see in diagram, our dataset has also 667,000 unique words, with average of 6 words in each sentence. The distribution of words is 5 to 15 in each sentence. Although we could prepare the dataset, but also we should test the performance of neural networks with it. So we tested newly created dataset on 3 neural networks. I'll talk more in next slides. Gated recurrent unit is the next generation of long short-term memory that can understand short sentences as well. In the first model, we use GRUs to test our dataset. As you can see in picture, autoencoded structure has two parts: encoder and decoder. Input sentence tokenizes with a pretrained tokenizer. Then tokens enter to an embedding layer, and GRU are waiting for outputs of embedding to extract most important features from them. This action repeats in decoder part for paraphrased sentence. After that, the outputs of encoder combine with output of decoder with flow vector. The dense layer are responsible to train how to make target sentence from input. Also, this model is not powerful to understand complex sentences. Transformers are pioneer in the NLP tasks. They are big, powerful, and complex. In this neural network, we can train the model in two ways. The first approach is to train the model from scratch, and the second is to fine-tune the pre-trained model. In second approach, we have a model that has trained before, and we can use the previous parameters as starter parameters to catch the goal faster and avoid getting stuck in local optimum. As you see in this picture, transformer structure starts from scaled up product attention, then it changes to a multi attention and then combined with the autoencoder model as we explained in previous one. This is the encoder layer that has 11 parts, and this is the decoder of transformer that has 8 parts. Setting the hyperparameter is important. Setting the hyperparameter is important. For training from scratch, we set learning rate like the original paper. During training, the further it goes, learning rate decreases because we don't want big change in last epochs. We use Adam Optimizer and the Spark categorical cross entropy loss function. Now we arrive fine-tuning step. We choose a T5, one of the best models in text-to-text generation. The structure of T5 is a simple vanilla autoencoder, but the creators trained it for text-to-text tasks, that we can use it as pre-trained model. We also use PyTorch framework that has published from Facebook AIT. You can see loss function change in both approaches. The loss function got better. These are real examples from random inputs and the outputs from different models. We try to use same inputs to set off potential of different models level. We tested our model with human evaluation. As the usual human evaluation, several people evaluated the sentences produced by the network in the fields of structure, meaning, correct paraphrases, fluency, and the creativity, with number between 0 and 5. We randomly selected 100 sentences, include 30 sentences from Twitter, 30 sentences from everyday conversation, 20 sentences from networks on trained dataset. Totally, we provided these 300 sentences to 5 people to evaluate in 5 areas. These 5 people include a literature teacher, a data scientist, a doctor, an accountant, and a hairdresser, which of these fields is either 0 or 1. A totally meaningless sentence got 0 and a completely correct paraphrase sentence got 5. As you see in the table, fine-tuned transformer got better marks in mind of evaluator. Actually, we found these models have some problem with complex sentences, and they also have problem to generate meaningful structure and different sentences from input. Okay, this was our work, and thanks for your attention. Any question?